Hi guys, welcome back to lesson 2. So we're going to be talking about energy, and in particular 2 types of energy that we will be working on in this unit. And so recall, energy is the capacity to do work. So there is an equation, we didn't really mention it, but later on we will do more, is that work is actually change in the energy. And if you remember from yesterday's lesson, we know that work is F delta D, and we know that the unit is also measured in joules. So that means energy, the unit is also measured in joules. So the first type of energy that we're going to be focusing on is called the kinetic energy. And the definition is kinetic is like moving. And so when they talk about the kinetic energy, it's basically anything that is moving, it will actually possess its energy. So that's why if someone have a moving softball and they throw it and it hits you, it will hurt because it does possess energy. Okay, so the way that the kinetic energy is derived is basically come from the equation work is force delta D. And I'm just going to write it all out just to make sure that we're good. Okay, at this point, we're just going to assume the angle is zero. It's like 90 degrees. Like we're just assuming that the force is parallel to the displacement. So we're not going to worry about the cos theta. So to start out with the equation, we know that work is force times displacement. And since we know that force is m times a, so when we sub in the force into here, we know that work is also mass times acceleration, which is the force, times the delta D, right? Okay, then the next thing is we're going to go actually and look at the kinematics equation. And I don't know if you remember this kinematics equation, but it's the V2 squared equals V1 squared plus 2A delta D. We're trying to derive another equation that has to do with speed. And since we are noticing the relationship of A and D, if we can take this equation and rearrange the equation for acceleration time displacement, then we can actually throw it into the work equation and see where it leads to us. Okay, so let's just rearrange. If I want A and D to be on its own. Okay, so if this is what I wanted to be on its own, does it make sense that I have to bring this over by subtracting first? So V2 squared minus V1 squared is equals to 2A delta D. So to get A delta D on its own, what I'm going to have to do is I'm going to have to get rid of this 2 to the other side by dividing. So what I have right now would become V2 squared minus V1 squared all divided by 2 equals to A delta D. Then what I'm going to do now is take the A delta D and we're going to throw it into the A delta D over here on the other side. Okay, so work is equals to mass. So instead of A delta D, I'm going to plug in the V2 squared minus V1 squared over 2. Okay, so throw it into here. So V2 squared minus V1 squared over 2. We're going to try to expand it out. So first of all, the divided by 2, I can make it with each of the V's. So W is, I'm going to leave the M for now. Okay, I'm only going to work within the bracket and then I'll expand it in afterwards. So it's the same thing as V2 squared over 2 minus V1 squared over 2, but don't forget the brackets. I'm only working within it. And then the next thing is we're going to throw this into, because there's it's a binomial, I have to expand and multiply both of them. So work is equals to mv2 squared over 2 minus mv1 squared over 2. I would like you to highlight this equation. Okay, so this is the first equation that will be helpful for you. Okay, so I'm just going to call this equation number 1. So work is equals to mv2 squared over 2. So the mass times the final velocity squared divided by 2 minus the mass times the v1 squared over 2. So let's see where this leads to us. Okay, so that's just I just did it all, and so this is, if you want to read it through, that's how we got it. And then we can decide that if v1 is 0, see how the v1 term is gone. So this is your second equation that you would need. This is equation 2. Okay, so grouping them all together. Okay, so let's just rewrite them. We said that work is mv2 square over 2 minus mv1 square over 2. And since we know that EK is mv square over 2, some people like to write it 1/2 mv square. It's up to you. I mean 1/2 mv square. Do you see how it's the same thing? So that's just a variation. If you want to put the 2 at the bottom or times it by 0.5, it's the same thing. When I divide something by 2, it's the same thing as multiplying it by 0.5. So it doesn't matter. So if I know EK is 1/2 mv square, I don't know if you can see that work is also EK2, final kinetic energy, minus initial kinetic energy, or change in kinetic energy. See how, because final minus initial is the change. So these are all the variations of the same equation. Okay, so this W equation ties with the beginning. If I'm going to go back to slide 1, do you remember how we said this one, right? Work is change in energy, and we've gone through all the math, all the proofs to tell you that, yeah, this is true. Work does equals to the change in energy. Okay, so because work is change in energy, that means EK is also measured in joules. Okay, so now let's start looking at example. Calculate kinetic energy of a 150 grams baseball that is traveling towards a home plate at a constant speed of 35 meters per second. So this is probably kind of one of the straightforward questions. Tricky. SI unit. Grams is not the SI unit for physics, okay? I know in chemistry we use grams a whole lot, but it's kilogram that we're going to have to use, okay? So let's start writing. I'm looking for what is the kinetic energy, with the mass being, you can write it out at 150, but I would change it right away to divided by, so remember you have to divide it by 1,000 to go from grams to kilogram. And then they tell you the speed is 35 meters per second. Equation for kinetic energy is 1/2 mv squared. So 1/2 mass mv square. Nothing tricky with this question. My biggest problem is people always, could sometimes forget to do the point through the square. So answer worked out to be, doesn't look right, times 0.15 times 35 square. So 91.875. I need 2 significant digits, so 92 joules. Okay, so that's the answer that I'm getting. So work and kinetic energy, and we already talked about the net work done to change the speed is equal to the change in kinetic energy. So work is EKF minus EKI with the change of kinetic energy. So it depends on what is given in the question. If they give you like the initial speed and the final speed, you're probably dealing with a change in EK. So I know work could be the final kinetic energy, and I know that kinetic energy is 1/2 mv squared. We already talked about that just now. 1/2 mv squared and minus EK1, and that could be equals to change in kinetic energy. And don't forget, from the class before, sometimes they might not directly give you work. They could be giving you work by force and delta D. So there are all these different connections that you could make, but this is in general the equations that you could get. So let's see what the next question talks about. Okay. A 165 grams hockey puck initially at rest is pushed by a hockey stick on a slippery horizontal ice surface by a constant horizontal force of magnitude of 5.0 newtons. What is the puck's speed after it moved for 5 meters? Okay, so I got the mass, SI unit, don't forget. So I'm going to put it in SI unit by dividing it by 1,000. It was initially at rest, so V1 is 0. And it has a constant force of 5.0 Newton. What is the speed V2 after it has been pushed for 0.5 meters? I have mass, there's force involved, so we can use work is force times displacement. But I also know that work is change in kinetic energy. And these are the two that we're going to be putting together. So F delta D is going to equals to the change in kinetic energy, meaning the final kinetic energy minus the initial kinetic energy. So force is 5, displacement is 0.5. Half, are we okay that if I sub in half mv squared, and this is the final, minus the 1/2 mv1 squared. So that's just because I know, you don't have to write it out, but I just want to remind you, since I know that EK is 1/2 mv squared. Okay, so I'm going to have to sub it in. Okay, the next thing that we're going to do is now sub in the number. I know that V1 is 0, so that means that whole term is gone. So 5 times 0.5 equals 1/2. The mass is 0.165 V2 squared. This is the part I need you to pause your video. I need you to figure out how to rearrange the equation for your math to figure out V2. So pause the video, figure out your V2 before you come back, okay? Try it out. What did you get? Oops. So I got on my calculator that the V2 is 5.5. So 2 sig is what I'm keeping. So I got it to be 5.5 meters per second. Okay, I'm just gonna, on the side, just to make sure you guys are all good. You can skip this if you got the answer, that's great. Okay. So if I'm just going to go to this one side and just rework it out. So 5 times 0.5, you don't have to show all the work. To be honest, I could jump from this step right to here. You can do it all on the calculator. But if I want to, I can write them all out just to make sure that everybody's on board. 1/2 0.165 V2 squared. Many different ways you can do it. You can punch this in the calculator and figure out what it is. But what I do, if I do it all one shot in the calculator, okay, I would write 5 times 0.5. If I have that half, I'm actually going to multiply it by 2 on the other side. And then I need to get rid of the 0.165. It used to be multiplying. So now I'm going to have to divide everybody by 0.165. And that equals to V squared. So that means I need to take the square root of it to figure out what your V2 is, okay? If you need to go step by step and write out multiple steps, do that. But hopefully eventually you can just do it all in one step and then it won't be, it will be fast. So now the second type of energy we're going to talk about is this thing called gravitational potential energy, okay? Potential energies means store energy. Energy that is possessed by this object store inside. There is many different things that has a store energy, like a battery. It stores energy in it. You can trigger it to do something like light up your light bulb. Gravitational potential energy has something to do with gravity, okay? It's basically by lifting something high up, okay? It's going against the gravity. So the definition is it's a form of energy that an object possesses because of the positions relative to the force. Okay, so due to its positions relative to the surface of the earth, when you lift a penny and you lift it really, really high up, when you drop it, when it impacts the ground, it will strike and make a sound. It will hurt if you actually drop it from a very high spot, okay? Because the energy that is possessed by the coin for you lifting it, you're storing the energy, and when you let go, the stored energy can turn into something else. And one thing to keep in mind is that gravitational potential energy is always determined from a reference level of your call. You're the person who decide where the zero is. So basically, reference level is where the 0 meters is in your question. And you're the one who is making that up. Okay? And I'll show it to you when we get to the example. Okay, so similar to the kinetic energy, gravitational energy can also be derived from work. And they didn't write it out, but we already actually did it in lesson 1, but I'm just going to do it again. So remember, work is force times displacement. When I have an object and I lift it high up, the force that you have to go against is the force of gravity. And since I know that the force of gravity is m times g, we're going to sub it into the F in this case, which is m times g. And instead of calling it delta D, we call it a delta H, right? It's the height that you have now lifted. I went from 0 meters to whatever height it is. So instead of calling it delta D, we call it work equals to mg delta H. How far did I lift it? And so we can conclude that the energy, Eg, this is the new one. So gravitational potential energy, we call it Eg, and it's mg times H. And so if I were to write out the work, I don't like this one. They really should. Can you change this to delta H? Because it's not, work doesn't equal to mgh. Energy equals to mgh. Work is always a change in energy. So this becomes mgh2 minus mgh1. So work is Eg2 minus Eg1. Okay, so these are the same thing, a variety of it, but I need you to know Eg is mgh. That's a new equation. So today you've learned, 4 new equations. We're going to sum it up very quickly. Okay, first equation is work is changing kinetic energy. Also, work is changing potential energy. So work is changing energy. And we know that potential energy, Eg, is mgh. And we know that kinetic energy is Ek equals 1/2 mv squared. And finally, this we'll talk more tomorrow in the next lesson. Mechanical energy, sometimes they use the word called total energy. Okay, and we call it the EA. You'll be like, what does A mean? It means that at this point A, like say if I have a roller coaster, okay, the roller coaster is at a certain height with a certain speed. We know that the Ek, they said that in here, mechanical is the sum of the kinetic plus the gravitational potential energy. So at each particular point of a system, we know that the total mechanical energy is the kinetic energy at point A plus the potential energy at point A. And we'll learn how to do that tomorrow. Okay? So going back to just using the example of gravitational potential energy, the question asks you, what is the gravitational potential energy of a 48 kilogram student at the top of a 100 meters high drop tower relative to the ground? So you have a tower, okay, and you got a student that's right here. And relative to the ground, meaning the ground we call the H equals to 0. What is the potential energy there when the height is 110 meters? Okay, so that's what relative means. Relative means I make that 0. The ground is relative to the ground. I make the ground 0, and then I do the measurement of the height relative to that 0 point. So the question asks you, please find the gravitational potential energy if I have a mass of 48 kilogram and if I have the height at 110. And equation for Eg is m times g times h. So 48 times 9.8 times 110. So So work that out with 2 sig digs. So 48 times 9.8 times 110. So 51744 joules. And take a look at the question. I want 2 sig digs, so 52,000 joules is the answer that I'm